Okay, so I think we'll start up again, and I'm gonna start here. The material before this was a review of the current mirror and the very basics of the common source amplifier. So I jumped to a few of those. You're welcome to review that stuff on your own. But I'll start with the common source, and we'll spend a bit of time on it because it's a very important circuit in its own right, being used increasingly much because when the supply voltage is very limited here, let's say it's 1 volt or even lower, you don't have room for very complicated circuits really in order to accommodate minimum biasing required to keep Q1 and Q2 in saturation, and as well still allow for some swing to appear at the output. You really can't do much more than have two transistors stacked on top of each other. So it's also, the common source amplifier is also, the analysis of it provides the basics of the differential pair because it's an equivalent half circuit for differential pair, which is a really important circuit. So lots of reasons why we're going to review this. So here you just see some basic small signal equivalent representation here, and then here the Miller theorem is applied to split this CGD capacitance into an equivalent capacitance at the input, most importantly. So, the method of zero value time constants is reviewed here, but I'll skip over that and just highlight, what it means for the common source amplifier. So here we're just finding the three time constants. Tau 1 is the time constant of CGS, of the input transistor. Tau 2 is the time constant of the output capacitance, C2, which includes the parasitics associated with Q1 and Q2, but also the load capacitance. And then finally, you've got Tau 3, which is the capacitance or the time constant associated with CGD. So that's fine and all, but I want to, really emphasize the two main possibilities, two main possibilities that arise most often in the design of common source amplifiers, integrated circuits. So one is where the time constant and the input is the dominant one. Specifically, the time constant associated with the Miller capacitance. So you're familiar with this. The Miller effect causes this CGD to kind of look A times bigger at the input. So in some cases, that Miller capacitance at the input combined with, and especially when the source resistance of the preceding stage, right? So if you like, that could be the output resistance of whatever's driving this gated Q1. That time constant together, in many cases, is dominant and limits the bandwidth of the circuit. So for that to be the case, as I said, typically it would mean that RS is not small, and also that CL is not big. Okay? So under that circumstance, what would be the considerations in your mind as a designer? Well, if you need to achieve the most possible bandwidth, okay, for a certain allowing yourself only a certain amount of current. How would you achieve that? How would you size Q1? So, since the bandwidth is totally determined by the input time constant, it's therefore proportional to CGD. CGD in turn is proportional to the width of transistor 1, right? Because it's like the overlap capacitance between the gate and drain. So, if you want to increase the bandwidth, presuming there's nothing you can do about RS because it's from the preceding stage, what do you want to do? You want to minimize W1. Okay? For a fixed current or fixed GM, let's say you want a fixed gain. In either case, those are two different situations, but in either of those cases, making W1 smaller means that the effective gate source voltage, or the overdrive voltage if you like, is increasing. Okay? So this is the situation where, for more bandwidth, keeping all else constant, you're going to want to bias Q1 with a large overdrive voltage. Why? Because that gives you, for the same GM or the same current, that gives you smaller parasitics, smaller W1. And that's what's limiting you in this case. The other case is where you're limited more at the output. So this arises especially where you're driving a large capacitive load. There's a lot of circumstances where CL is governed by other considerations, often governed by noise considerations, right? You may be familiar with the noise on the capacitor. It's KT over C in a lot of circumstances. It's not quite the case in the simple circuit, but still, noise is inversely proportional to capacitance value. So if you need low noise, you need a large capacitor. There's no way around it. It's physics. So in that case, you may be totally dominated at the output node. So in that case, the situation is a little different. For a fixed current, for a fixed current budget, gain and bandwidth are going to be maximized by, first of all, whatever your current budget is, use all of it in the transistors Q1 and Q2. Okay. And secondly, you're going to want to have a small bias with a small V effective one. For your current budget, that translates into using a large value of W over L for transistor 1. Okay? Because as we do that, right, V effective will come down as we make the transistor wider. Now, how is that going to help improve the bandwidth of the circuit, right? You might be wondering that seems to contradict what we just talked about. By making W of transistor 1 bigger, we're going to increase all the parasitic capacitances associated with it. But in this case, it doesn't matter because I said CL was by far the largest anyway, right? So even if you double the capacitance of Q1, CdB of Q1, for example, it's still a tiny fraction of CL, right? In that case, go ahead. Instead, what you would get in exchange for that, for the same current, as we know from our previous discussions, is that you get more GM. So if GM1 goes up, that's going to give you more gain, okay? And it's not quite clear, perhaps yet, how that turns into more bandwidth. It doesn't directly impact the 3dB bandwidth of the circuit, but what it does improve is the unity gain bandwidth of the circuit, right? So basically, if you have a frequency response like this, by increasing GM, you get more DC gain for the same bias current. So that's gonna shift out. That can help shift out the unity gain bandwidth here, where you cross over. Okay. And in the specific case that's going to be of interest to you, when this picture really is representing the equivalent half circuit of a differential pair, let's say, and that differential pair is part of an op-amp, it's the front end of an op-amp, let's say that's going to be put in feedback, it's actually the unity gain bandwidth that's more important of the amplifier in determining the bandwidth of the closed loop amplifier as a whole, right? Yes. The closed loop bandwidth will be proportional to the open loop unity gain frequency. You're talking about if you have a fixed amp, and by playing with the feedback around that amplifier, you're right, you trade bandwidth for gain. Okay, but here we're not closed the loop yet. I'm just talking about, like, before you do that, basically what I'm saying is you want to design the amplifier to have the highest unity gain bandwidth you can, and then you're going to trade off with that unity gain, keeping that unity gain bandwidth what it is, right? So here what I'm talking about is the way to design the amplifier itself to have the highest possible unity gain bandwidth is going to be to design with a small V effective. Now with respect to Q2, really it's just the active load for Q1. So there's no incentive to increase its GM or transconductance really. The only, the primary incentive here is therefore to minimize the parasitics associated with it. And so you would do that with a larger V effective. There's actually a secondary motivation why you might want large V effective for Q2, and that is because it'll result in less noise at the output as well. So for, we haven't talked about noise yet, but for a common source amplifier and many related amplifiers, right? Because you see that many of the other high gain amplifiers are kind of derived, they're kind of improvements on or derivatives of a common source amplifier. That's a pattern that you may want to keep in mind, that the transistors that are providing the gain or the transconductance gain, then you're trying to use them, the bias current in them efficiently, and you do that by having a small V effective typically, unless the transistor starts getting so big that it's hurting you, right? On the other hand, all the transistors that are not being used for gain, not being used for transconductance gain, they're just kind of there for biasing or as loads. Those you typically, unless you have time for further analysis, you would kind of first pass assume that they should be biased with a larger V effective, right? For the two reasons I mentioned. Okay. So here we're, it's showing a diff pair. Again, small signal analysis is quite related to that of the common source. So we'll kind of skim through this. Here's a numerical example showing, showing the voltage gains that you might expect. But I want to get to this part here, cascode gain stages, okay? So two types of cascode gain stages, the telescopic cascode and the folded cascode. I think it's can be at first glance sometimes a little bit intimidating or complicated to look at a folded cascode, but just keep in mind, always recognize that both the telescopic and folded cascodes are basically a common source amplifier or a common source transistor, Q1 in both cases, followed by a common gate transistor, Q2 in both cases here. And so it just so happens that on the right, the common source and common gate transistors are of opposite type. And in order to accommodate that, you kind of have to flip the biasing around a little bit, right? But that's why small signal wise, we're not going to deal with them separately. In terms of their small signal analysis, the NMOS and PMOS transistors kind of the same small signal model, so there's no difference. So why might you prefer one over another? There's a few different reasons. The fact that one interesting difference to note is that in a telescopic cascode, both the common source and common gate transistors share the same bias current. So whatever bias current you choose, that's the bias current for Q1 and Q2. Whereas with a folded cascode, you have this kind of extra degree of freedom that you can choose to bias one transistor with more current or less than the other. You also have this other strange degree of freedom, which is that you may prefer to have the common source transistor be of one type, and the common common gate transistor to be of a different type. So that's another thing. These are things that'll, the way you use these degrees of freedoms will become more clear later on when we talk about the folded cascode op-amp. But if you were just looking at it purely in isolation, I mean, there's some clear benefit to the telescopic cascode, which is exactly what I just mentioned, the fact that it reuses the same bias current, right? So whereas in the case of the folded cascode, the total current coming from the supply is the sum of the bias current you need for Q1 and Q2. For the telescopic cascode, the total bias current being drawn from the supply is only one of those, right? They're the same. So, you know, just even purely simplistically, you can imagine that the bias current and therefore the power consumption of a telescopic cascode could be kind of half that of a folded cascode. That's a big deal right there. Yeah. Right. So that is something that is unfortunately it's a little hard to illustrate when we're just talking about single-ended versions of these circuits. It becomes more clear when you have a differential pair version of these. But briefly, you can have a significant drawback of the telescopic cascode is that you have less swing available to you here. And it's not truly the case with a single-ended version. And again, it only becomes clear when you have to put the tail current underneath Q1. So just briefly, when you have if you make this into a differential version, the telescopic cascode, you now have to accommodate a current source up at the top, which is probably two transistors stacked on two PMOS transistors stacked in a cascode. You have to accommodate two NMOS transistors stacked in a cascode. And plus you have to accommodate the tail current, all telescopically connected, right? So again, it's both a good thing and the bad thing about it. The good thing, it means the same current's running through all of them. You're reusing the current nicely that way. But the bad thing is that you don't have much voltage left over for swing here. Okay. On the other hand, with a folded cascode, it's Q1 that's the input transistor, so the tail current fits here. So you have fewer transistors stacked on top of each other. The direction in which you have most transistors stacked is actually over here, right? But the thing this is where it gets a little subtle. You should recognize here that whereas on the left, I suggested that you'd probably want two transistors stacked for I bias in a cascode. Here, you've really already got one of those PMOS transistors there. So you only need one transistor up here, one PMOS transistor. And looking up from the output, you'll still see two. You'll still see kind of a cascode, right? So you basically save one transistor in the stack. You still need two NMOS transistors here, but on the left picture, you need 5, and on the right picture, you need only 4. Okay. So that buys you a couple hundred millivolts extra swing, which is precious if you've only got 1 volt total power supply, right? But, you know, as I said, sorry about that, but it's a little bit, maybe I shouldn't have even bothered, but it's a little bit easier to see when we start talking about differential pair circuits. But for now, I just want to highlight, you know, some key points. This is output swing. We already actually summarized this on the last slide. This is just gain analysis, small signal analysis of the cascode. But here I want to spend a bit of time on this one to consider the two primary cases. One is where, case 1 here on this slide, is where we load the transistor, load the cascode stage with a single PMOS transistor biased in active mode here. Right. So in that case, we would see a resistance that's kind of like RDS of a PMOS transistor. Okay, so that's what's indicated here. So in that case, what it means is that the total gain we expect is only GMRDS, which is similar to what the same, very similar gain to what you would see with just a straight common source amplifier, where you'd have even more swing available, right? So you only got the 1 transistor there instead of 2. But we'll see later that case 1 is most useful because it can have a higher bandwidth. We'll see that in another slide. Than its common source counterpart. Case 2 is where we connect 2 PMOS transistors biased as a cascode, they're both in active mode, as the load. So in that case, we have a much higher output resistance looking up into the cascode. Okay. So you see something like a GMRDS squared, right? So it can be larger than case 1 by a factor GMRDS roughly, which is sort of like the gain of a transistor. So significantly larger load resistance. So here is where you get the much higher gain, right? The output, now you've got GM times a much higher output resistance, R out. So effectively you get the gain of 2 transistors, or 2 stages, from 1, which shouldn't be surprising. It's because in some sense you do have 2 stages. You've got a common source and a common gate, right? So you're kind of getting the gain of both of them stacked on top of each other in case 2. But then in case 2, you would say, why don't we do that all the time? First of all, you have less swing available because now you got 2 PMOS transistors. And secondly, you lose some of the bandwidth benefit that you get from case 1. You see that when we do the time constant analysis. So in either case, right, starting from a telescopic or a folded cascode, the small signal representation of both of these are the same. And you can do the time constant analysis, and you get, the key point here that's of interest is the way the cascode transistor impacts the Miller effect. So the Miller multiplier, the factor by which CGD1 is kind of increased by Q1, by the gain of Q1. Remember, that Miller multiplier relates to the gain that is seen across the 2 terminals of the capacitor, not from input to the output of the stage, but across the capacitor itself. So what you see then is that really the Miller effect, the Miller multiplier, is just being multiplied by the gain of one part of the cascode, just the common source part, right? So, what that means is that the 2 cases that we just talked about are very, very different. Okay, let me see if I can go on. Oh, I'll have to go back to show you this. These 2 cases we talked about are very, very different. Because in the top case, Rin was very small. Rin was kind of a 2 over GM. Okay? Which means that the gain from here to here is the gain of the Q1 is really just GM1 times Rin2, so something like 2 over GM, which means you've only got a gain of about 2. So, if you compare it to a common source counterpart, that would give you a very similar voltage gain, GMRDS. The common source amplifier would have a Miller multiplier of GMRDS because the gain is being seen across these 2 nodes. The cascode transistor in this case is kind of shielding the capacitor CGD. It's shielding it from the amplified signal at the output, right? So it means that the Miller effect the Miller multiplier is much, much smaller. VS2 is basically hardly moving at all in case 1. All the gain is showing up here at the output. It's appearing across Q2 instead. If you recall, a common gate transistor, a common gate stage, doesn't experience the Miller effect. So that's why I said even case 1 is interesting and useful. It's often used, for example, in LNAs or something like that, low noise amplifiers. It's not that you're using the cascode in that case to get extra gain. You're actually using it to get more bandwidth because it ameliorates the Miller effect. Case 2, the gain between across CGD1 is basically the same as what it is in the common source, similarly biased common source stage. You get the full gain GMRDS across there, and then you get another GMRDS going across Q2. So there you get the extra gain, but the Miller effect is just as bad as it would be with a common source. And the difference, remember, between case 1 and case 2 is what load you connect. Whether you connect a really high impedance load or a low impedance node. Okay. So that's main kind of intuition I wanted to to get out from the analysis of the Cascode transistor. And then now these next few slides are some, I think, very important ones. They're just basically general principles about biasing. Now that we've seen, we're kind of reviewed quickly the basic stages, I think it's easier to see how the biasing of an individual transistor, the biasing and sizing of it, affects the most common stages that we're going to be interested in: common source, cascode, their differential equivalence. Right? Those are the main ways you have to think about that we get gain, analog gain from a MOSFET. Is we use the small signal transconductance that's inherent in it, basically the fact that modulating the gate changes the drain current, right? So you take that GM to generate a varying current, and then you try and push that current through a big impedance. That's how you get gain. Because MOSFETs on their own, unfortunately, don't really look like voltage amplifiers, right? They look like transconductors. So you use them as a transconductor and you push it through a high impedance. So, with that in mind, right, it's really instructive to just think about each MOSFET in isolation as having a kind of built-in intrinsic gain to it. Intrinsic gain can be thought of as the most gain you could ever get from one MOSFET, most voltage gain you get from one MOSFET on its own. So how would you get the most gain you could from one MOSFET? You would bias it so that it's in active mode. You would supply the drain current over here with an ideal current source. So it's got infinite output impedance. And then you modulate the gate, and that would give you the small signal current GM VGS. And then the only load that transistor sees now, because we've biased it with an ideal current source, the only load it sees is itself, its own small signal RDS. So in that case, you've got the full gain of the transistor, this full voltage gain, if you like, of the transistor. It's intrinsic gain GM times RDS. So here we've substituted in expressions for GM and RDS that are assuming that the thing is biased in active mode and we're still respecting the square law. So there's an assumption there that we're keeping it in square law regime. But if you do that, right, you see I used this particular expression for GM because it simplifies the product a lot. It allows you to cancel out the drain current, interestingly. And what you see is that the intrinsic gain depends basically only on V effect. That's the only thing here that as designers we have control over. Lambda is like a transistor parameter. Which unfortunately varies quite a bit, but we don't really have much direct control over it as designers. The only kind of free variable we have as designers is V effective, which we influence by changing the amount of bias current in the W over L, right, in the transistor. So it doesn't matter whether you talk about a transistor with 1 milliamp or 2 milliamp drain current. If you if you also increase the W over L, you double the W over L in those two cases, you end up with the same intrinsic gain, same gain in those two stages. So that's a key insight here. It doesn't depend on the drain current if you keep the effective the same. It also tells you right away that you get the most gain from a transistor at the lowest V effective. Right? So that's something that we already hinted at. Basically, it's because RDS doesn't change much if you keep the current the same and you just change the size, the W of it. Key point here. I think I was a little bit misleading there. So that's one point. For the most gain, you would bias with the smallest V effective, right? I was a little misleading when I said that you don't have direct control over lambda as a designer. That would be the case, assuming that you wanted to stick with, for example, the minimum length transistor available. You'd be keeping L constant. You can influence lambda if L is allowed, if you're allowed to change L, basically, if you allow yourself to change L. So that's important. Lambda varies in inverse proportion to L. which means that if you are, let's use the word allowed, right? If you allow yourself to increase L, that's another way in which you can increase intrinsic gain of the transistor. So here's an expression. Sorry, we don't have the expression that substitutes that in. But the key point is that if all you cared about was gain, what would you do? How would you size W over L? Let's say the drain current is fixed. Someone says I'm only giving you 100 microamps to spend over there. Nothing you can do with that. How would you size the transistor? You would first of all make L huge, okay, as big as you can tolerate and still maintain a reasonable bandwidth that you need, right? And then once you had the biggest L that you could stomach, you would increase W until you're basically right on the verge of subthreshold, right? You would increase the ratio W over L. That would decrease the effective all the way down to like 100 millivolts, 70 millivolts, somewhere around there. And at that point, what happens? This equation is no longer accurate. Instead of 2ID over B effective, it becomes ID over NKT over Q, right? Which is just constant. And so then you're stuck. You get diminishing returns at some point. There's no point making it any bigger. So here in this slide, we define something about the intrinsic speed of the MOSFET. So this is kind of looking at the speed trade-offs involved in sizing and biasing. So a couple different ways to think about the speed of a MOSFET, but one commonly used metric is its unity gain frequency. In fact, if we were being really precise, we should always say unity gain or unity current gain frequency. When you say that, the definition is kind of clear. It means this frequency at which a small signal current gain from gate current to drain current to small signal gate current to small signal drain current becomes only 1, right? So in case, you need reminding, right? You might say, well, I thought there's 0 gate current. Well, not at very high frequency because, of course, you've got capacitances here, right? So at high frequency, there is AC current going in and out of the gate, right, to drive those caps to make the gate node wiggle around. So, and at some point, at some really high frequency, it takes a pretty large amplitude current to wiggle that gate up and down. And at some point, you're delivering basically the same amount of gate current as what you're getting out of the GM times VGS, right? So that's kind of a frequency beyond which you start being kind of silly to even think about the transistor. You just use a wire, right? So that's where, why you might care about the unity gain frequency. Also, you'll see in some analog amplifiers, like the folded Cascode differential amplifier that we'll talk about later, some of the parasitic poles in that amplifier, some of the poles in that amplifier are directly related to or directly proportional to the FT of the individual transistors in there. So they also are related to, you might say this is kind of a fictitious thing. I'm never going to use it at that frequency, whatever, right? It's true, but this quantity is in turn ends up being proportional to quantities you do care about once you put it into an amplifier. Those pole frequencies will be a fraction of this FT, a fifth or something like that, but still proportional to FT. So whatever you do to maximize FT is going to help those amplifiers as well. So how do we get the, just like for the case of the intrinsic gain of the amplifier, right? We hooked up some biasing around it that would allow us to measure the full gain, right, of the amplifier. So basically we used an ideal current source to bias it. So by the same token here, to do this test, if you like, if it's in simulation or the lab, you try and bias it in a way that allows you to see the full current gain of the amplifier. So the best you can do in that regard is make the drain a small signal ground, right? So that you've got no funny time constant going on, no swing at the drain, right? That might impact, that might create a Miller effect, for example, at the input. So the lowest, the fastest case you could ever get is where the drain is at a small signal ground. So in this case, we bias it with an ideal voltage source instead of an ideal current source. Okay. Now, if you do, then it becomes a very simple small signal equivalent schematic here. And you can find the gain from I in to I out. It's just GM VGS, right? All the output current goes there. So really, the frequency at which you've got unity current gain is the frequency where I in equals GM VGS. So you can equate those two, right? And you end up with this really simple expression here. It's GM over CGS, CGD, the two parasitic gate caps on there. So if you substitute in then the square law expressions for GM and capacitance, gate capacitance, right? So here the approximation that was made is that we kind of assume that CGS is bigger than CGD. Not a great assumption. It's not necessarily way bigger than CGD, but anyway, it captures the important behavior, because if CGS gets bigger, CGD is also going to get bigger, so you get the proportionality right. And we need this expression over here to allow us to get the design insight out of it. So when you do this expression, you see some interesting stuff. GM is proportional to W over L, but the gate capacitance is proportional to W times L, right? The gate area. So what that means is that the W's cancel, but the L's, you end up with an L squared in the denominator. So in terms of speed, there's a clear benefit to using the smallest possible gate length. You get this squared in the denominator, which is why, of course, right, with progressing CMOS, the transistors get faster. But that's exactly in conflict with what we saw for the intrinsic gain. Intrinsic gain, you want a larger L. For the speed, you want the smaller L. The second interesting thing you see is that the V effective shows up in the numerator. So why is that? Well, it's basically just saying that for a certain amount of drain current, obviously you're going to be better off if CGS is small, which means you're going to want W to be as small as possible as well. Basically, all this expression is saying is make that transistor as small as you can, right? Make W small, make L small. But it's nice writing it in this form because you see now the effective is in the numerator, whereas just back a second ago it was in the denominator. And L over here, it is in the numerator for gain, whereas over here it's in the denominator. So it clearly illustrates, right, the trade-off, the gain bandwidth trade-off. Then there's a third case that's of interest here, which is not really a property of the transistor on its own, but I pointed out as well to avoid some confusion that arises later about, well, how do you maximize the speed of an amplifier, right? Again, it relates to what load you're driving with that transistor. So the intrinsic speed, right, it was appropriate to do this, but we assumed that the load was this ideal voltage source. There's no capacitance there, nothing. We just want to see the speed of that transistor on its own. But if we're in a situation where the transistor is driving a capacitive load, CO, that is actually way bigger than all the parasitics at the input. It's a common case. Then what happens in terms of the gain? In terms of the bandwidth? If that's the case, this situation I'm referring to here is the extrinsic gain bandwidth, or the extrinsic speed, because unlike the intrinsic parasitics of the transistor, this one depends on a load that's extrinsic to the transistor itself. So in this common case, you see that the unity gain frequency that relates I in to I out now depends on very much on the load, right? Being the dominant capacitance. So the unity gain frequency, I want to draw it out. Here's GM, VGS. And it's driving this load CO. That exhibits a gain, which at low frequency might be depending on RDS, but that at a high frequency starts coming down, right? As the impedance of CO decreases, you get this point at which, if we write this in terms of radians per second, right, that's the frequency where GM over CO, because the gain is GM, the frequency dependent gain is GM times 1 over J omega CO. Okay, if I neglect this RDS at high frequency. So if I equate that with unity, then I just have to flip the thing around and solve for this unity gain frequency here, omega extrinsic, and you see that it's just GM over CO, and then there's just this factor of 2 pi in there to make it F extrinsic. Okay. So actually I should have, this figure's just obviously copied from the preceding slide, but really you should bias this with go back to biasing this with the current source. Otherwise the voltage source just shorts out CO. Okay, small signal. So here this paints a very different picture than the intrinsic bandwidth. The extrinsic bandwidth, if it's proportional to GM over CO, and we substitute in over here, what we did is substituted in GM equals 2ID over V effective. You get this expression down here, which tells you that you're back to the situation where you want to minimize V effective, right? And therefore you want to make the transistor big. So the reason that makes your speed better is because it doesn't matter that the parasitics of the transistor get bigger. CO is what's limiting you anyway, so you might as well make it bigger, and that allows you to take advantage of the fact that you have more GM. Right? So you see that, right, of these three situations we talked about, what you care about is gain, right? The key takeaway points I want to emphasize is, if what you care about is gain, that suggests you should bias with a low V effective. If what you care about is extrinsic bandwidth, then what you should do is bias the low V effective. The only case where you would, which we said is pretty much always means that you're around weak inversion, like 100 millivolts of overdrive voltage, something like that, somewhere around there. And then you can play fine-tune from there at least. The only case where you would bias with a high V effective is where there's no parasitics that are causing, no other load parasitics connected to the transistor that are significant. So really then, in that case, the intuitions there is pretty simple too. Yeah, sure, then you want to make the transistor tiny if what you care about is speed. So this is just summarized here, right? Gain is maximized with low V effective and large L. Intrinsic speed is maximized with high V effective and small L. And then extrinsic speed is maximized with low V effective and large ID. Okay. So last section here is about variability and mismatch. So this is an important point, but it doesn't actually take long to communicate. I know we only got 10 minutes, but it doesn't take long to communicate this. First thing is, when we talk about variations and mismatch, I think it's worthwhile to always be precise when you're talking to other people about it. There's many sources of variations of like the values of components on an integrated circuit. There's systematic, and I kind of categorizing them in these three buckets here. Systematic variations are the ones that are observed repeatedly and consistently. If you make 1 million chips, for example, you might always see that this resistor is a little bit bigger than that resistor, let's say. So why might that happen? And I'm considering the case where you nominally want them to be the same, and yet you make 1,000,000 of them, and on average, this one is always 2% bigger than that one. You would expect random fluctuations to average out when you make 1,000,000 of them. But why might that not happen? The main reason is that you didn't lay out the circuit perfectly symmetrically in some way, right? And that can be the case for whether it's MOSFETs, capacitors, or resistors. If there's any asymmetry at all, and sometimes it's hard to avoid. I mean, let's say you've got to hook up, this circuit to another one that's off to the right. Well, how can you make it totally symmetric, right? In the end, the output's got to go to the right, not the left. Right? That's a simple example, but it's things like that that introduce systematic variations. So that would be like a variation, kind of like from what you expect, when you cut the schematic. Process variations are different. That just arises from manufacturing variability, right? And those are really important. So you see that in the assignment, there's sections of the assignment that we're going to require you to simulate your circuit with different process variations. And the way that's handled in practice is that you have totally different device models. You have a set of device models that's the typical ones, right? That provides nominal values for all the parameters like Cox and mu and so on. And then you've got what's called fast and slow models, which vary all of those parameters in unison in whatever way makes the transistor a little bit faster and a little bit slower, right? And then finally, there's random variations. Okay, random variations are the ones that often are referred to as colloquially as mismatch, something like that. The idea here is that on any given chip, okay, obviously all the transistors on that chip, all the resistors were manufactured at the exact same time, and so there's no process variability from one to the other, right? But still, there's just going to be some statistical variation from one to another on the same chip, just because of, let's say, variations in dopant concentrations from one part of the chip to another, or we talked about gradients that can arise across the chip. All these things, right, can cause random variations. So here's a couple of specific examples, just to illustrate how these things can creep in. Here's an example of a systematic variation, which is that basically when manufacturing the chip and you're implanting an N-well into which you're later going to come along and put PMOS transistors. So how do you do that? Well, you create this blocking layer, a photoresist layer, let's say, that's grown on top, and then you do the dopant implantation step. But it turns out that right around the fringes of the well, some of the dopants get scattered. They don't just get blocked or reflected, they get scattered and end up in the well. So around the edge of the well, you get the dopants that came directly, and you also get a few of the dopants that were supposed to be blocked that got scattered in. Whereas in the middle of the well, you've got only the dopants that came directly in. So you can end up with a slightly higher dopant concentration around the edges of the well. And this is not a small effect. What it means is that you take this well, now you're going to go and fill this well with a bunch of PMOS transistors, and the transistors that are close to the edge of the well can look very different than the ones in the middle of the well. I've seen results where you have to leave 1, 2, 3 micrometers away from the edge of the well before that effect disappears, which is a really big number if you imagine the transistor gate might only be way less than 100 nanometers, right? So and that's an example, and that's nothing that's evident when you draw a schematic or anything like that. That comes way later. Someone lays it out. And the antidote for stuff like this is basically just to leave a bunch of space or to design a circuit that's tolerant to it, right? Specifically, it changes the threshold voltage, by the way, is what it does. Other stresses, right, they have to do with layout. These are the examples of systematic stresses. When you have interdigitated fingers of a MOSFET like this, they're all fingers of the same transistor. They're not then isolated from each other. Right? These insulating trenches are not introduced between fingers of the same MOSFET. But wherever you have a gap from one MOSFET to another, these isolating trenches are introduced. And the way they're manufactured, right, when these trenches are etched into the silicon, it creates stress on the crystalline structure immediately surrounding the trench. Even without being an expert in physics, not hard to imagine, right? So that stress, that strain that's put on the crystalline structure, changes the carrier mobility around there. So again, what it means is that the transistor over here has a little different properties than the transistor over here that's impacted by this stress on both sides. So this is called STI induced stress. That's the source of it. So STI stands for shallow trench isolation. Okay, STI induced stress, again, hard to predict when you just put down a schematic, but it comes later. It comes later when someone does layout. And in fact, both of these examples I gave, typical post-layout extraction tools won't even tell you about them, really. So really, that's why I said the antidote in the previous case was just to do the layout to avoid it. In this case, similarly, what is typically done is you put a couple of dummies at either side of the transistor and just don't use them. Don't hook them up. And then only use the fingers that are kind of in between the trench regions. Process variations, I'm going to go quick. Just to point out, right, these terms are used every day, fast and slow. What do they really mean? Slow means high VT and small values of mobility and Cox. So why does smaller capacitance mean slow? Again, it's because GM is proportional to Cox. Don't forget that. So even though the gate capacitance might get smaller, you're losing GM as well. And usually that means it's a slower circuit. So that's what slow and fast mean. And of course, there's even second and higher order parameters that are also being varied, but that's the key point there. So lastly, sorry, we're going to end up with only a few minutes for this, but as I said, it's really not rocket science. It's the idea of the random variations of the mismatch, which basically there's this so-called Pelgrim model for mismatch named after the first author of the paper that introduced it. And it basically says that if you have a parameter P of a component on an integrated circuit that you care about, could be the sheet resistance, could be Cox or mu or whatever, some parameter that you care about of some components, the statistical variation of that, so it's going to vary with a Gaussian distribution on random, just because of random stuff that goes on. That was the model anyway, okay? And the sigma of that Gaussian is going to be proportional to two things. It's going to be inversely proportional to the area of the transistor or capacitor or resistor, whatever it is. So the bigger you make it, the idea being that these random variations kind of average out if you make the thing huge, okay? And the second thing is that the amount of variation between two copies of the same component is going to increase with the square of the distance between them. So two components right next to each other will have, this term can kind of go away and vanish. But if you start making two transistors far apart, the amount of variation will increase. And then these other two parts of the model, these are just constants that really have to do with how accurately that process can build that component. That's all. So those are, they have to be given to you basically by the foundry. So this is the idea, right? dx is the distance between the components, and W times L is its area, whether it's a MOSFET or whatever. So the main variations that we care about with transistors, the main parameters that we care about with transistors, and that we model in this way with the Pelgrim model, are their threshold voltage and K prime, remembering that K prime is the product of mu n Cox. Because to some extent, we don't care whether mu n is going up or Cox is going up. As analog designers, those two changes kind of look the same to us 99% of the time. So we typically model variations in those together and just give it one constant, one set of constants, AK and SK. Okay? So when we get closely spaced devices, this is what I was saying, so specifically with a common centroid layout, which we already talked about, the second term can go away. And then all you're left with is this first term, which is inversely proportional to area. So in the assignment, you're asked to look at a current mirror. Okay, and to size W and L of these transistors to achieve a certain matching. So you're given the constants that govern, the mismatch. The assumption is that you're putting these things right next to each other, so there's no distance term. The distance term goes away. Okay, so don't worry about that. You're given these two constants, the one that governs the random variation in the threshold voltage, and the one that governs the random variation in K prime. And you've got to size W over L so that the currents match a certain percentage. Okay. So the main purpose of this, the arithmetic here is one thing, which is not that complicated, but actually it's a bit of a challenge. It's something you may or may not have done before to simulate this, right? So it's a bit of an exercise just to figure out how to set up a simulation where the transistor parameters will vary randomly, and basically the approach that's used is to conduct what's called a Monte Carlo simulation, which basically means you simulate 100 times with random variations on these parameters. And that's the final sanity check that says, yes, I've sized it right. Like with all analog design, the idea being that you would do some back of the envelope calculation to get confidence that you're kind of doing the right thing. But then in the end, you've got to show your boss a simulation that shows, look, I did it right. I did that calculation right. Don't believe me. Here, I ran the simulation 100 times, 100 Monte Carlos. And what you see is that these currents always matched within 5%, whatever the number is. Okay. So I'm just pointing out, that's part of the assignment. I know that it's a bit of a pain to set up a Monte Carlo and run it, but that's the point, is to make sure that you've done that and know what it looks like and how to interpret